Retrieval-Augmented Generation is powerful and it's being successfully applied to multiple use cases across industry. And based on my experience, a lot of use cases I have come across mainly apply RAG into text data. And in reality, we have more than text data. We have like images, tables, audios, even videos. What if we could leverage RAG and apply that to those types of data as well? This is where multimodal RAG can be helpful. In this video, you will learn how to apply multimodal RAG to a real case scenario. And in this specific case, we'll build a RAG system that helps ESG specialists to retrieve relevant insight from those type of data for better decision making in their investment process. Okay, this is the overall workflow of what is being covered in this video. Like any RAG framework, we have two main components. The first one is retriever and the second one is the augmented generation. Let's have a closer look at how these two components work. First of all, the analyst is going to send a query to the retriever, and during the retrieval section, the analyst query is embedded by an embedding model, and that embedding is going to be used to perform a nearest neighbor search to find the most similar objects within the vector database to the user's query. And those most relevant objects are going to be combined to create a context. And that context is sent to the generative model to generate the response to the user. And before all that, we have, in our use case, we're using audio data, also tables and images. Let's start with the audio part. We are downloading video from YouTube, and that for each video, we are going to convert that specific video into an MP3 file. And that MP3 file is used to generate its transcription using Whisper model by OpenAI, which is an open source model, by the way. And at that level, we have a textual representation of that audio file. And the second type of data is mainly PDF, and inside that PDF, we have different components. And the first component are tables containing multiple types of information. And that table is used by a generative model as well to perform a description of what is inside that table. And the second type of data that we deal with is image, and we are going to basically apply the same approach to images. Since we cannot directly use images, then a generative model, the same generative model, the one that we use for tables, we are going to use the same model to perform, generate the description of what is inside that image to create a textual representation. And finally, we also have the basic text in that PDF. And at this level, we will have a normalized data of all the initial data. They are all going to be textual information. And once we have those text data, we use the same embedding model. If you recall the embedding model that we have used during the first stage, that same embedding model is used to generate the embedding of all these textual data. And once we have those embedding, the idea is to get them into the same multimodal embedding space. Let's say that we have in our documents, either it's audio or PDF. Let's say that we have something related to labor practice and other objects related to human rights. You will see that labor practice and human rights will have the same level of similarity compared to climate change and air pollution. Climate change and air pollution, on the other end as well, would be closest compared to these two. This is where it becomes interesting to have that similarity in the embedding space. And once we have those vectors along with the metadata that we have generated from the original data, all this is going to be stored in a vector database, and in our use case, it's going to be a Weaviate vector database. And once we have everything in the vector database, now it will be easier to perform the similarity search and generate the final result. So this is basically the overall workflow of what is going to be covered. So let's jump in on the notebook to proceed with the actual technical implementation. Before getting into any similarity search, any response generation, we first need to have data into the vector database. And that starts with data collection. And the first step is in our scenario to collect data from YouTube, generate the MP3 representation. It's basically this section. We're starting with this section, basically. Okay, so to do that, we have the YTDLP library that is used to collect data from YouTube. Okay, after the installation, we can now import the library using the YouTube DL module. So here it says pip dependency resolver does not currently. This shows like an error, but in reality, it's not an issue for the successful installation of a library. So you can completely ignore this part. And we also import two additional modules like OS to perform some operation system analysis, and RE for regular expressions tasks. So here is the class that I have implemented to perform the YouTube audio download processing. Basically, we have two main functions, actually three main functions. Let's start with download audio. To be able to successfully download audio, we specify these parameters: format, which is best audio, you basically provide these details for the module to successfully consider the quality of your data during the downloading process. And now we are using the YouTube DL module to perform all the processing from data download to renaming the file with the MP3 extension. And here we are basically showing some information telling whether the audio has been successfully downloaded or if there is an error. So this function download a single file. And in our case, we might have multiple videos to download. This is where we use that download multiple audios. Download multiple audios is using this function. And here the get save file name is used basically to change the file naming that is going to be stored. And once we have this, we run this one, and here we have two main videos that we want to download in the data folder. So the input of the class that we're using is a folder, and this is where the final downloading is going to be stored. And we run the downloading, and in the end we print the message showing that the files have been downloaded. So let's run it. Now you can see that we have two audio files, the first one and the second one. Okay, now let's get back here. Now that we have the audio, the second step is the transcription, this section where we are taking each MP3 file and transcribe that into the textual representation. And this is achieved using the Whisper model. Whisper is an open source model made available by OpenAI, and we are using Whisper. First, we need to install OpenAI Whisper using the pip install command. By the way, the reason why I'm using -QQQ is for the installation to be performed in a verbose mode, because sometimes when installing libraries, it shows a bunch of details that we don't necessarily need. So that's the reason why I'm using -QQQ. Okay, this installation might take a couple of minutes, depending as well on your internet speed. All right. Once the installation is successful, now we can import operating system. Actually, we have already imported operating system, so we don't need it here anymore. We have Whisper, we import Whisper, and we also import Torch. So import both Whisper and Torch. And after we have imported those two modules, here is the class responsible for performing the transcription of a given audio file. And it has two main functions. The first one, which is transcribe audio, and the second one is using that first transcribed audio to transcribe a list of audio files. So we have the transcription. Let's have a look at the first function. This first function is performing a check whether a given audio file exists in the folder that we have provided. It's using those analysis and whether the file is existing or not. And here is where the actual transcription is occurring. We use the Whisper model .transcribe function, and that transcribe function takes as parameter the audio file that we want to transcribe. And once the transcription is complete, then we return the text field of the transcription. Otherwise, we raise an exception saying error in transcribing the audio file. And the second function, transcribe all audio, is taking a dictionary of audio files, which is going to leverage the first function to run the transcription of all those individual files. So we run this class, and before running the transcription, we need to specify whether the device, we set the device to CUDA to use the GPU, or we use CPU, because those models are very heavy and it might take long time to load them in memory and run the actual transcription. And here I'm using the medium size of model, but in Whisper we have different model sizes here. We have a tiny base, small, medium, and large. So medium is what we are using now. What is interesting to note, to understand here, is that the larger the model, the longer it's going to take to load in memory, and also the better the quality it is. If we had to take the tiny model, the loading process will be very fast, but the quality of the transcription would not be that great compared to larger models. And it's like all compromise depending on your use case, whether speed is more important to you than actual accuracy. Getting back to that, we run this. All right, and at this level the loading is complete. And once we have a loading complete, now we are specifying the folder containing our MP3 files, which is the data folder. And now we initialize the Whisper model, and now we can run the transcription, which is taking the audio files. And let's run this. As mentioned earlier as well, it might take longer to generate the transcription of each MP3 file. All right, at this level, we have the transcription for each MP3 file that we had. And here in this print section, we are printing the URL of the audio that we had, the actual audio file, and its transcription. We're just showing the first 100 characters of that audio file here. Let me show you the transcription dictionary content. From the transcription dictionary content, this is the field that we are retrieving here, and here we get that transcription field. Now we have the full transcription of that specific audio here, and it's a lot of text. Actually, a lot is being said during that discussion, depending on the use case that we are solving, because in that use case we want also the model to provide additional information like the URL of the video that is being discussed, the path of the audio, and also the transcription. So what we do here is to create that metadata in the form of a list of dictionary. So every time we have the response of the model that is contained in that video, then we are also providing the link of that video, the path, the audio path, and this is the transcription that is going to be used. In here we have the corresponding results, the link, the audio path, which is contain that data. Here is the full MP3 file with respect to these folders, and the same for the second audio, and also the transcription of both. At this stage, we have completed half of the data preprocessing. We're now done with the audio parts. To recapitulate, we have downloaded video from YouTube, created MP3 files of each video, and then generate the transcription. In the next step, we are going to cover this section, and this specific section is about extracting the main components that are tables, images, and also raw text data. And for tables, we are going to generate the summary of a table, and the same methodology applies to images as well. Let's start what is going to be covered in this section. Basically, here is the overall description of what we are going to cover. It's almost what I have explained in this video, so let's move on. Here we are installing the main components that are required to perform the PDF processing. And as you can see here, we have multiple modules, and here, like, the reason why I'm putting % bash is like, without this I will have to put like this sign and do the same for each pip install. So instead of doing this, I am installing everything and considering this as a bash command. So this is going to run all the script without the need of specifying the exclamation mark. After completing the installation, now we need to also install Tesseract OCR. Since we are dealing with PDF files, so we need to also install the Tesseract OCR module using the following section. All right, and now we run this section as well to install those libraries. Now we can proceed with the use of the unstructured library. Unstructured library is a very powerful library, and it allows the efficient processing of PDF files. Let's see, we'll see that in this section. So from unstructured partition.pdf, we import the partition PDF function. And also, once we have that module imported, now we specify the PDF file that we want to process. And the PDF file is this one. This is a 43 pages PDF that we want to process. And here, as you can see, we have like text data, we have table, we have graphs, we have more graphs, tables, and so on. This is basically the structure of this PDF. And what we are doing here is what we are going to do is to extract tables, these tables, images, like corresponding to these graphs, and also text components. Text components will be these textual data. Wherever we have text data, we are going to extract that as text. And the remaining, this is a table. So this is going to be in the table section. This one as well is a table. It's going to be in the table section, and that one as well. Okay, so this is what I meant by extracting the components of a given PDF file. Now we also install Popular. So without Popular, we would not be able to perform the preprocessing. Popular is the backend for PDF processing. Now we install Popular as well. And once Popular is also installed, now we can perform the processing using the partition PDF function that we have imported from unstructured. So here we have a couple of arguments. We have the file name, which is the file that we want to process, our PDF report. The strategy, high resolution. This is going to extract all the components in high resolution format, especially for images, and extract images in PDF. True, we specify that in true, so that the function consider extracting those images from the PDF. Extract image block to payload. We set this one to false because it's not going to be that relevant for our analysis. And here we specify the output location where the extracted images need to be saved. And this is going to be in the image folder, which is currently empty. And now we run this one. Now we can see that the images folder has all the images extracted from that PDF. Okay, and now let's see what the ESG report raw data looks like. And here we have a couple of components. We have elements, I will say, the header element, figure caption element, images, title, narrative text, title, narrative text, and so on and so forth. So what we are interested in extracting are images, narrative text, and tables, right? So image correspond to the components representing images. So every time we encounter element that image, it means that that component is an image. Then we'll be able to retrieve that component as an image. The same apply to narrative text. Every time we made a narrative text, then we know this is a text component. Then we retrieve that. The same applies as well to table. Every time we see element.table, we know that component is a table. So this is how unstructured makes it really easy to extract component from a specific PDF file. Now we can proceed with the extraction of each component. Let's start with the text components, which is this portion, this part of the workflow. First, we import from unstructured, we import the narrative text. With narrative text, here is the helper function that I have implemented. It takes the report, the PDF reports, as the first argument, and the second one is the source document. Source document is basically the path of the PDF documents that we are processing. And the final result is a dictionary with the following details: the source document, which is I have mentioned, the PDF file, the page number. Every time we extract a text, we also want to know which page did that text document belong to, the paragraph number, because on a page we might have multiple paragraphs. We also want to know which paragraph does that specific piece of text belongs to, and the actual text. The reason why I am specifying all this, because it will be really important when the model is giving a result to be able to provide along these details, granularity details, which is also going to help for verification purpose as well, because the model telling that the answer to our question is this answer might not be enough, because we would like to know more details where that text has been extracted from, which page number, which paragraph number, so that we can go straight to those locations and check if the model is wrong or correct. That's the reason why I am implementing this logic here. So getting back to the whole logic, here is if the element in ESG reports, this is basically the whole bunch of information that we have extracted here. So every time an element is in that report, and if the element is an instance of narrative text, then we retrieve it. We first get its page number and its paragraph number, and we store those details here. Let's run this function and see what it looks like. And here we are providing those details, the raw data and the ESG report path. Let's run this to see what it looks like. And the extracted data, here we have the extracted data. For the first one, let's have a look at the first one. And here we have a lot of information actually. The text has a lot of data. The first, the source document is going to be the same because we are processing the same PDF file. Page number 1, paragraph number 1, text April 25th, 2024. April 25th, 2024. The model said has been extracted from page 1, which is April 1st, this part, April 25th, 2024, and 2024, yes, 2024. And the same logic applies to other sections. On page number 2, this section of the text has been extracted from page number 2, and it's in the second paragraph. You see, this can be really, really important for the model when giving results. Once we have extracted those components for text, then we come to the image part. And similarly for text, we also use the image component from unstructured elements. We run this one. And here is the helper function as well. And for a given image, we provide the source document, the page number where we have extracted that image from, and the path of that specific image. And here, like, the logic is the same: page number, the image path, element that metadata, that image path. This is going to be the path of that image, and we are running a loop to add everything in a list, and at the end we have a list of dictionaries of those components. Now we run. So like for all the images that we have extracted from this folder, here is a helper function that is basically going to loop through this folder and print all the images. And for each image, we show the page number where that image has been extracted from. So this is what that logic is implemented in this helper function. And now we can run with display image. The display image function, which is, like I said, going to display all the images along with their page number. Here we have all the images. The morning star, which is this logo here, is on the first page. And we have this first graph, which is in page number 3. Let's check where page number 2, page number 3. This graph has been extracted from page number 3, and that one as well from page number 4 all the way down to page number 36. So we have extracted all the images. And what is next after extracting the images? Now we are also going to extract the tables component. The table component, you'll see that this is really similar to the image part. And for table as well, we are extracting the tables, source, the page number, the table component, which is the text component from that table. And we are extracting the tables part. And the additional section here is that we need to generate the image summary and also the table summary. And for that, since this use case is being applied to ESG, then we need to have a model that is a specialist, an ESG specialist. And to have a model that is an ESG specialist, that is done through the prompting. The prompt that is going to be used, we have two different prompts for those two types of data. We have one prompt for table and another prompt for images. Let's take things step by step. First, we need to install OpenAI, LangChain Core and LangChain OpenAI. OpenAI is going to be leveraged to use those LLMs that we need to provide with the prompt. So here is the prompt that I have specified. As an ESG analyst for emerging markets investment, provide a concise and exact summary of the table content. Focus on key ESG metrics like environmental, social, governance. It's also important to specify what ESG means, because for the model, it might have a different understanding of what ESG means. So for the model to be accurate, you want you as well to be as concise and precise as possible. This is the prompt that I'm providing, and here is the placeholder for each table that I'm going to evaluate. And for the description, I'm telling the model to limit its summary to 3 to 4 sentences, ensuring it's precise and informative for ESG analysis in emerging markets. So first, let's install those first two modules. All right, once the modules are installed, we already have the prompt. Run the prompt, and we import the chat completion, which completion prompt template and chat OpenAI from the models that we have. And now we are importing as well the credentials OpenAI API token, which is saved in the key sections. So in key section, you'll see that we have those credentials here. Let me pull this one here. We have the OpenAI key. So I have specified the key here. We have the name of the credentials and their values here. So OpenAI key, to retrieve that key, I'm using the user data.get function and provide the name of the key. Yeah, the name of the key we want to retrieve the value. And this is done by importing Google Colab that user data function. And at this stage, we run this, which is going to retrieve all these information. And now we need to run the description model. Description model is run. And here is the helper function that is going to generate the description of a given table. We have three main inputs. The first one is the ESG report, the source document, and the table summarizer prompt. The prompt that is here. And now we first start by creating an empty list. On that empty list is going to contain all the dictionaries that we are creating for each table. And each table will have four main like information. The description, which is going to be the textual description. This part, summary. By description, I mean the summary. The textual description generated by the model. The table content, which is the raw content that we have previously extracted, the page number, and the source document. And for the description part, we have the description model, the one that we have here, that predict messages, message.content. So this is going to retrieve the actual content that has been generated by the model based on the prompts that we have provided. And let's run this function. And with that, we apply that to our data, and this is going to run for each table in the data and the PDF file, creates the description for each one, for each table that we have in the documents. The extraction is, the processing is complete. Now, let's see the extracted table with summary, what it looks like. Okay, the source document, page number, table contents. So here is like the actual raw data that we have extracted from the table. As you can see, like it's not that easy to understand. And here is the description generated by the model. The table reveals that emerging markets, specifically Asia ex Japan, show modest ESG investment inflow at $0.2 billion. So this is basically the textual representation generated for the table that is in the second page. The model is actually giving the summary of this table. So it's giving the description what is in this table. So instead of getting that, like the content here, we are asking the model to generate the textual description of this table. This is what we've done here. This is what the model has done here. And for page number 5, it's doing the same, applying the same approach. Overall, actively managed, passively managed, and so on. So here we have for each table its description. And let's have a look at the first description here. First description, I mean the first table along with its metadata, like the source page, page number, and the content. Here is what we retrieve for a given table. And that first description is here, if we want to have more details on that text. So what we've done here for the table, we are doing the exact same thing for images as well. The image prompt as well. As an ESG analyst for emerging markets, please provide a clear interpretation what's in this image, and so on, and blah, blah, blah. So this is going to use the same approach applied to the images. If image is in str element, then we are extracting those components, and the expected data for an image is base64 encoding, the description, which is generated from the prompt, the image path, page number, the source document, and in the end we are returning the image data, which is the list of all these dictionaries here. Okay, and similarly to the previous step, just run this section, which is going to loop like in the PDF file and extract all these information: source document, page number, image path, the description from the LLM that we have specified, which is GPT-4o model being used, which is, I believe, the latest model by OpenAI at the recording of this video. Image data. Now let's see what is in the image data. For image data, we have similar data format. Like, it has the same structure as the table format, table data that we have. The sixth image detail. And we're getting the details of the sixth image. We have a source document, page number 4. That image is in page number 4, image path. The description of the image, it says this image, the image described appears to be an infographic illustrating ESG performance metrics for various emerging market countries. So page number 7. In page number 7, let's see what is in that image. It's this image that is being described by the model. The key element may include country-specific data points like carbon emission, social equity indicators, and governance quality ratings. All right, and here is the full description. And now we have completed this whole data processing. This whole data processing is complete. Now we have all the data in textual format. They have all been normalized as a text. So the next step is to upload those data into the vector database. But the vector database that we're going to use here is the Weaviate. And here we have to first install Weaviate client. Weaviate client is installed using the pip install. And Weaviate client is installed. Here as well, I've noticed that it's saying errors, not like package does not currently take into account all these packages that are installed. But like, the installation is still successful, and I don't know why this is being considered as like an error, even though the installation is successful. Let's verify it here by importing Weaviate. And as you can see, we are able to successfully import Weaviate, so there is no issue with that. First of all, we need to create a Weaviate cluster, because to be able to upload data in the vector database, we need to create a cluster that would host our vector database. And to complete that, we first need to log in on Weaviate. And what I'm doing here is completely free, so nothing of charge. And log in on my account. Login attempt failed. Okay. Why though? Let me see that. Okay. The login is successful. So first we create a cluster. And for the cluster, just come to free sandbox. That free sandbox is going to provide 14 days lifetime use. Like, it's going to be available for 14 days. And now we give the sandbox a name. Let's say this is ESG data. ESG data. In that ESG data, now we can create a cluster. Region is required. Okay, I'll take in US East. That's my region. And now create. Depending on where you are, so you select the corresponding region so that it gets closer to where you are. For someone living in Europe, you might choose the region, like European region. The reason for that is to reduce latency so that you can efficiently access your database. Now this sandbox is created. Here now we can get the credentials for the cluster. To be able to connect to the vector database, we need two main credentials. We need the link and also the API key. So where can we find those details? Here we have the link. This is the link that we're going to use. So we copy that link and save that link into the credential, the link section. And now we get the API key. Here's the API key that we copy, the admin API key. This link will not, those keys will not be valid right after recording of this video. So, and here is the API key that I want to put here. And now, once we have all those credentials, now we can create. For the client, we use the connect to WCS function from Weaviate. Cluster URL, we give the link of the cluster. The authentication credentials, this is going to be using the API key that we have provided here. And OpenAI API key, this is the OpenAI API key that I have already set up in this part. The connection is created. Now we have a client. The client is nothing but an object location. We have the Weaviate client, that's Weaviate client, which is located at this address. And now we need to specify the structure of the data being pushed into the vector database. And to do that, let's first have a look at this. Push this one here to have more space. All right. So when pushing data into a vector database, we need to define what are the properties of the data being pushed in that vector database. And for our case, we have these properties as specified previously. For each document, we have defined a specific types of properties. And we are kind of bringing all these properties together to create a single set of properties. And for each property, we need to tell Weaviate which one to vectorize and which one to keep the vectorization for. And here, when doing the analysis, we might not want to vectorize the source document because it's not relevant, right? We might not also want to vectorize page number. So whenever we don't want to vectorize something, we specify skip vectorization to true. And now we need to create a collection. The collection is a placeholder for our data being pushed in the vector database. And I give the RAG ESG document name to that collection. And now we provide the properties that we want to save in that collection and vectorize the config to none. I have specified this one to none because I want to provide my own vectorization model, my own embedding model when uploading those data into the vector database. This is where it becomes very flexible. You can provide your own vectorization model here so that it's considered during the uploading process of your data into the vector database. This is going to automatically create the collection. Now we have, let's refresh this one, and we might see in the collection section the collection that we have created, RAG ESG document, and it has 12 properties. These 12 properties are exactly those that we have defined here. Now that the collection has been created, now we can proceed with the ingestion of the data. The ingestion of the data I'll start with a couple of helper functions that I have implemented for each function, for each type of data, there is a specific ingestion function. And now I'm specifying the text embedding tree large model by OpenAI. I could use like any types of embedding, but I just decided to go with this one because it provides great accuracy compared to some of the embedding models. And here is the ingestion function for audio data. By ingesting the audio data, we are providing the link, like all the metadata specific to audio files, the audio path, the transcription, and the content type, which is audio. This is a new field that we are adding, and it's going to be useful moving further. And here is the vector. The vector that we are getting is the embedding of the audio transcription. This is going to generate the embedding of the audio transcription. And now we create, like, this is going to be a batch of adding all these data. And we do the same for text data. For text data, where the embedding is occurring is here. We get the vector and we do batch adding as well. The same apply to images. For images, we are also providing all the data, vector, image description. This is the vector for the image, and the content type is image. For table, the same thing, exact same thing applies to tables as well. And each of these individual helper function are combined into a single function, which is ingest all data. Now let's run this to be able to use all this helper function. So we have here ingest audio data, ingest text data, and so on, ingest table data. And at the end, we either successfully do the ingestion or fail to ingest the data. And now we start the ingestion in the collection that we have created, which is the RAG ESG document. All right, as you can see, it has been pretty fast for the audio text, like the audio data, because we have only 2 audio. But for text, we have a chunk of text that we have extracted from PDF. Reason why it's taking more time compared to the previous one. And that might be the same as well for images and also tables. Now we have successfully completed the ingestion of all the data. Now let's have a look at the first object in that collection. In that collection, we're going to get the first object along with the vector. So we get the collection iterator, include vector. This is going to include the embedding of the object that we are retrieving. We get the collection. So we have a content type, which is text, the transcription, none, because of course we don't have a transcription for text. We only have transcription for audio. So the transcription is none. The text, the actual text is given here. Table content, this is not a table, it's a text. So table content is none. Source document, we have a source document. Image path, once again, this is not an image, so image is none. Like, if there is a property that is not specific to that data, then that field is going to be none. And now we have here the default part. The default key is actually the vector key, and the value is the embedding from the text embedding tree large model. So this is going to be the same. It's very long. It's going to be the same structure for every object that we have in the vector database. Now that we have ingested data in the vector database, we are currently at this stage where we upload data in the vector database. Things have been already uploaded here in the vector database. Now we can start with this part where we get the user's query, embed the user's query, and perform the nearest search from the vector database and retrieve the top and relevant chunks. By chunks, I mean objects from the vector database. So this started with the Weaviate query. We create a Weaviate query, search multimodal. This search multimodal is going to perform exactly what I have briefly described here. So first, to get the collection that we want, the first step is to embed the query, which is the analyst query. Here we get the embedding. So get embedding model text tree large is going to embed the user's query, and we get the collection where we want to search for the similar objects. The response is esg.query.nearVector. That near vector is going to get the most similar vector to the query vector, which is the representation of the embedding of the user's query. And we want to include the distance. Distance here is like the inverse of the cosine similarity, because if we take the cosine similarity of two vectors, the higher the cosine, the more similar those vectors will be. But if we take the distance is like 1 minus the cosine similarity. So the lower the distance, the closer those two vectors will be. So I want to include the distance matrix as well, so that the users can see at the end that score to understand why the model has made that choice. And here is a helper function that is basically using this initial function to perform the proper formatting. It's going to print search query for the query provided by the user. For item insert, if the property is audio, then we print the link, the transcription. If the property content is text, then we print things specific to text, and the same applies to other types of data, image and table. Let's run this as well. And now we have the first query. What are the main environmental challenges in renewable energy? Let's see what this gives as a result. Here we have a query, the initial query of the user. The type is image. This means that, first of all, let's have a look at the distances. Out of these three results, this is because we have specified the limit to be 3, which means that the top n relevant n here is going to be 3. So we have the 3 most relevant documents, chunk from the result, from the vector database. The first one is here, they are both image. This means that the result is extracted from an image. And the source is the document that we have, the PDF, page number 13. This response comes from the image of page number 13. So the description of the image is here, this image appears, and so on. The distance is here. So at this level, what we're doing is just retrieve the most similar object to the query provided by the user. And at this level, we're not doing any response. We are not responding to user's query. We are just getting the top n relevant. And once we have those top n relevant, then we will be able to submit those n relevant documents as context to the generative model. And the generative model will now be able to generate the answer to the user. So this is where this section comes. So this section comes to the generation aspect. But before that, we need to define a prompt. How the model needs to answer to that a specific query provided by the model, by the user, sorry. You are an AI assistant specializing in ESG analytics for emerging markets. Use the following piece of information to answer user's question. If you cannot answer the question based on the provided information. Say you don't have enough information to answer accurately. So this piece of information is important. This is going to tell the model not to answer things it's not sure about. It's going to also reduce hallucinations. And here we provide the context which is the results. Here, these results are the context. And finally, we give the generative model that we are using is GPT-4 1106 preview. You can also use other GPT generative models. And here I'm setting the temperature to the lowest, 0, to minimize hallucinations as much as possible. And here is another helper function. So this helper function is going to use the previous functions. Like this is the retrieval section. Search results is going to search multimodal, use the search multimodal function that we have implemented here to get the multimodal result. And it's going to prepare the context for the RAG, because the RAG model, the generative part of RAG needs the context as well. So we create the context for each type of data that we have from the search result. And this is the final step, which is going to generate the results. This generation is happening from generate response, which gets the user query, that same user query here, and the context. The context correspond to the top and relevant documents that we have from the similarity search. And it's going to find the source for each type of documents. Depending on the properties as well, it keeps updating the source with the relevant metadata, the document, the page. If we have a text, we have the source document, the page number, the paragraph number. If the content type is image, we add page number of that image, where that image has been extracted from, the image path. And similarly to table, we also add the page number of that table. And now we run this one. So once we have this, we have the final output, which is user query, AI response, and sources. So from this level, we have something to provide the final output. But that final output can be formatted in a better way so that we can have a nicely understandable result. And this is done from using the analyze and print ESG result function, which also uses the text wrap. Let's install the text wrap module. The reason why I'm using the text wrap, it's to be able to properly format the text when printing. And text wrap, this help function, and now we have the analyze and print ESG result. And now let's have a look at the results. At this level, we have implemented everything. We have implemented the end-to-end pipeline. Now it's time to submit queries to the model and see how the model is going to answer that. The first question is ESG investment a fraud? Submit that to the model. User's query is ESG investment a fraud? AI response. Here we have AI response. AI responded based on the provided context. It's not accurate to categorically state that ESG investment is a fraud. The term frauds imply intentional deception, and so on and so forth. The audio transcription. See, the model is specifying that the audio transcription from the YouTube video presents a critical opinion that questions the effectiveness and sincerity of ESG investment. And here it's getting like the source. The type is audio. It's giving the source where the guy in the discussion is telling that ESG is providing his opinion about ESG.
Real marketing.
It's a complete fraud.
See?
Complete fraud.
It's so ridiculous. Governance has been addressed. That's useful. But, this idea that you're going to...
So as you can see here, like we have the result of the model depending on what it's understood from the context received from the similarity search. And the second one is the text. This is the most appropriate result, I will say. The second most appropriate result is here. So the result is given in terms of like decreasing level of relevance. The second one is type text. The document is obviously the PDF document that we are analyzing. And page 8, paragraph number 3, where the model took the result from. And here is another query. Another query asking, what was the total net inflow for global sustainable fund in Q1 2024? Here as well we have the user's query and the model's response here. The total net inflow for global sustainable fund in Q1 2024 was close to $900 million. Here is the source of the model provided by the model. We have distance of 0.162. The documents here, the page number is 2, the paragraph is 4. Let's have a look at that. Page number 2. Let's see what page number 2 holds in terms of result. So it says here we have the result from the model. It's stating exactly where the result is, $900 million inflow. The model is accurate. We have an accurate result. And it says in paragraph number 4, it's true we found the result, but is that paragraph number 4? Here it might be splitting the tables in terms of like understanding the paragraph. Maybe this portion is considered as paragraph number 1, number 2, number 3, and here is number 4. There is a process going under the hood in terms of splitting of the paragraph. But here I'll say the most important thing is the accuracy of the results and the fact that the model is able to tell which page to find the result from. And the same process applies to how did European Sustainable Fund flows perform in Q1 2024 compared to the previous quarter. Here we are running against the model and see what the model gives compared to what has been requested by the user. Here is the bunch of detail provided by the model, and it says page 6. Here's from the first quarter. The amount is $10.9 billion. Let's see on page number 6, paragraph number 2. So page number 6, here's the result. Paragraph number 6. I think it's struggling, even though it's providing the accurate result, the accurate page, there is an issue with the paragraphing, defining the correct paragraph. And this might need further preprocessing to make things more accurate in terms of paragraph. But overall, the model is giving the correct answer and also pointing to the correct page, which is awesome. Honestly, this is really awesome. Really awesome. And similarly, here this one as well. You can keep playing with other queries, ask questions to the model and see how it behaves. All right, this is really awesome. This is really awesome. And once you are done with everything, then you can delete your collection here by running client.collections.delete. This is going to delete the collection from the cluster that has been created. Well, this is all. We have come along a long way from understanding the overall workflow to implementing the end-to-end pipeline of getting this powerful system to be able to answer users' query and also providing the sources of those responses. Even though this has been applied to ESG, it can also be extended to other use cases, other industries. Well, this has a lot of potentials. It has a lot of potentials because it provides with more insights. It can give more benefits compared to just using text data. So if you like this video, give it a thumbs up. Let me know in the comments what you would like me to cover in my future videos. And bye for now. Thank you.